A strange signal pulses from a dead star. Across the galaxy, the dense, Earth-sized corpses of suns called white dwarfs are broadcasting mysteries we cannot explain. These stellar remnants should be silent, cooling embers, but they are instead sending out bizarre transmissions in light, radio waves, and even motion. This is a cosmic detective story, and by the end, you will possess a catalogue of 25 profound puzzles that redefine the final chapters of a star's life. We will encounter a world being shredded before our eyes and a magnetic monster spinning faster than a kitchen blender. These are not alien messages, but they are clues to phenomena so extreme they bend the rules of known physics. What does it mean when the grave itself begins to speak? The first signal on our list is a cosmic autopsy in progress. It comes from a white dwarf designated WD1145+017, a stellar corpse caught in the act of devouring its own offspring. Astronomers first noticed something was wrong when this star's light began to flicker in a strange, repeating rhythm. It was not a clean, periodic dip like a planet passing by, but a jagged, messy pattern of dimming that suggested something far more violent. The star's light curve, a graph of its brightness over time, revealed the truth. Swarms of dusty debris were orbiting in a tight, frantic dance, blotting out the starlight in an irregular cadence. This was the signal, a silent scream written in shifting shadows. The conclusion was both grim and groundbreaking. WD1145+017 is actively disintegrating a rocky planet, perhaps the shattered core of a former giant, its material stretched into a long, dusty ring by the white dwarf's immense gravity. This was the first confirmed case of such a catastrophic event, a world being methodically torn apart before our telescopes. Yet for all we have witnessed, deep mysteries remain. The precise composition of those debris clouds is a puzzle, with spectral signatures hinting at rocky and metallic fragments we struggle to fully identify. More perplexing are the forces at play. The debris does not move as simple gravity alone would dictate. Something else is pushing and pulling on these dust clouds, sculpting them in ways our models cannot yet replicate. Unexplained non-gravitational forces, perhaps from intense radiation pressure or even unseen magnetic fields, are actively shaping this graveyard. We are watching a planet die, but we do not fully understand the mechanics of its destruction. The second signal is a whisper of heat from a ghost. It comes from the white dwarf G2938, a star surrounded by a dusty graveyard, the remains of a shattered asteroid. For years, this seemed like a closed case, a static monument to a past cataclysm. But then astronomers noticed the infrared glow. This was the signal, a persistent and unmistakable warmth radiating from that dust. In the cold vacuum of space, dust should cool rapidly after a one-time collision. A constant heat signature means the dust is being constantly reheated. The only explanation is an ongoing bombardment, a relentless rain of fresh rocky debris falling onto the white dwarf's surface. Something is still feeding the machine. The leading theory points to an unseen architect, a hidden planet surviving the star's violent death. This perturbing world, with its steady gravitational pull, would act like a cosmic shepherd, nudging asteroids from a more distant belt into doomed orbits that end in a fiery plunge toward the star. It is an elegant solution, a hidden puppet master orchestrating this endless demolition. Yet after exhaustive searches, no such planet has ever been found. Its gravitational signature should warp the motions of the dust. Its reflected light might be glimpsed in the data, but the companion remains utterly invisible. This absence opens the door to far stranger possibilities. Perhaps the perturber is not a planet at all, but a recently captured rogue object, a nomadic piece of planetary debris from another star system, now trapped and causing chaos. Or maybe our understanding of the disk itself is incomplete. Could some unknown instability within the debris ring cause this cyclical bombardment without any external guide? The heat from G2938 is a clear signal of ongoing destruction, but the hand wielding the hammer remains a shadow, a mystery written in warm dust and gravitational silence. From dusty graveyards and ghostly heat, we shift to a signal of pure, crackling energy. Our third mystery is a rhythmic blast from the void, a repeating radio burst emanating from the white dwarf known as J1912-4410. This star is not alone. It orbits in a tight, frantic dance with a companion, a common setup in the cosmos. But what makes this pair extraordinary is their broadcast. Every few minutes, like a relentless cosmic lighthouse, this white dwarf unleashes an intense, coherent pulse of radio waves. For decades, such precise, repeating radio bursts were the exclusive signature of neutron stars, the universe's most dense and magnetized object. Their discovery around a white dwarf was nothing short of revolutionary. It was the first time we had ever seen this kind of behavior from a stellar corpse of this class, blurring a line we thought was firmly drawn in the sand of astrophysics. The signal is a direct challenge, a booming question mark. The mechanism powering these pulses is deeply obscure. One compelling theory points to an unimaginably strong magnetic field, orders of magnitude more powerful than typical for a white dwarf. In this scenario, the field acts like a colossal generator, siphoning material from the companion star and funneling it into focused beams that erupt as radio light. This would essentially make J1912-4410 a white dwarf pulsar, a theoretical creature that had only existed in equations until its signal was captured. But the details defy us. How does a white dwarf, with its different internal structure and composition, sustain such an energetic process? Is the companion star absolutely essential to the phenomenon, or could the white dwarf be powering this show almost entirely on its own? Each repeating burst is a clue that our categories for dead stars are insufficient, hinting that under the right extreme conditions, a white dwarf can masquerade as its far more exotic and powerful cousin. The boundary between stellar remnants is not a wall but a permeable membrane, and this radio pulse is the sound of something extraordinary leaking through. The fourth signal is written in disappearing ink. It comes from the white dwarf SDSSJ1228+1040, and its mystery is not about what we see but what stubbornly refuses to vanish. Astronomers study stars by breaking their light into rainbows, a technique called spectroscopy. Each chemical element leaves a unique dark bar in that rainbow, a fingerprint called an absorption line. In the spectrum of this white dwarf, the fingerprints are all wrong. They show the clear, strong marks of heavy metals, magnesium, iron, and calcium, elements that simply should not be there. A white dwarf's gravity is so immense, hundreds of thousands of times stronger than Earth's, that any heavy elements in its thin atmosphere should sink like stones in a pond, plummeting into the star's interior in a matter of days or weeks. Their persistent glow is the signal itself, a neon sign screaming that fresh metal is being constantly dumped onto the star's surface. This is the crime scene of an ongoing feast. But the plot thickens dramatically. These metal lines do not sit still. They shift back and forth in their rainbow, their wavelengths changing with a precise, repeating rhythm. This Doppler shift is the telltale sign of something in motion, something orbiting the white dwarf and dragging its cloud of metallic vapor along with it. The speed and proximity implied by this wobble are staggering. The source of this metallic rain is not a distant asteroid belt, but a single, dense object whirling around the star in an orbit so tight it completes a full revolution in just about 2 hours. That places it incredibly close, skimming just above the stellar surface. So what is it? The leading suspect is the solid, metallic core of a giant planet, utterly stripped of its outer layers, now a naked sphere of iron and nickel dancing a lethal tango with a dead sun. Yet there is a more exotic and utterly unprecedented possibility. The data could also point to a disk not of dust or gas, but of liquid metal, a swirling, molten river of iron orbiting the star. Such a structure has never been confirmed to exist. Is this the shimmering, vaporizing heart of a demolished world? Or are we seeing the birth of an entirely new class of celestial object, a forge of liquid metal born from stellar catastrophe? The shifting lines are a signature, but the hand that holds the pen remains hidden. The rhythm of destruction gives way to a rhythm of perfect celestial clockwork. Our fifth signal is a heartbeat, a flawless pulse of darkness emanating from a binary star system known as ZTFJ 1539 plus 5027. Here, two white dwarfs, both Earth-sized stellar corpses, are locked in an orbital embrace so intimate it defies belief. They complete a full dance around each other every 6.91 minutes. To put that into a human scale, in the time it takes to brew a cup of coffee, these two dead suns have circled one another entirely. The signal is the eclipse, a precise, rhythmic dimming of their combined light as one star passes directly in front of its partner, over and over again with the unwavering regularity of a metronome. This is not a messy flicker of dust, but a clean, geometric shadow cast by one ultra-dense world upon another. According to Einstein's theory of general relativity, such an extreme pairing should be a powerhouse of gravitational waves, ripples in the fabric of space-time itself. The energy lost to these waves should cause the stars to spiral inward, their orbit shrinking in a slow, inevitable death spiral. And indeed, astronomers have measured this orbital decay. The heartbeat is getting faster, the eclipses coming marginally sooner with each passing year, exactly as relativity predicts. Yet, within this confirmation lies a new puzzle. The timing of the eclipses shows tiny, persistent hiccups, minute deviations from the perfect rhythm that the simple two-body gravitational wave model expects. Something is ever so slightly tugging on the dancers, throwing their perfect timing off by a fraction of a second. This discrepancy is the whisper within the heartbeat. The leading explanation points to a hidden third actor in this drama, a distant, low-mass object like a planet or a brown dwarf whose gentle gravitational pull perturbs the exquisite clockwork of the binary. But after intense searching, no such companion has revealed itself. This opens the door to more complex and fascinating possibilities. Could the interiors of these white dwarfs, under such incredible gravitational stress, be flexing and deforming in ways we do not understand, creating subtle tidal forces that alter their orbit? Or is our model of how gravitational waves themselves drain energy from the system incomplete? The heartbeat of ZTFJ 1539 plus 5027 is the most precise stopwatch in the cosmos, and its tiny, unexplained stutters may be counting down to a revelation about the hidden forces at work when matter is compressed to its ultimate limit. From the precise clockwork of a binary heartbeat, we now encounter a solitary beacon of blistering, unexplained energy. The sixth signal is not a flicker or a pulse, but a steady, searing glare of X-rays emanating from the white dwarf KPD 0005 plus 5106. This star stands alone, with no visible companion to feed it, yet it burns with a ferocious and puzzling heat. The signal itself is a constant stream of soft X-rays, the kind produced by matter at temperatures so extreme they defy everyday comprehension. Analysis reveals this lone white dwarf has a surface temperature of nearly 200,000 degrees Celsius, a number that places it among the hottest stellar corpses ever discovered. This is the core of the mystery. A white dwarf of its age and mass should have cooled to a dim red ember long ago, its thermal energy radiated into space over billions of years. Instead, it shines with the fury of a much younger object, as if its internal clock has been reset or its flame stoked by some hidden engine. So where is this immense heat coming from? Astronomers are investigating several compelling yet unproven theories. One possibility is accretion from the void. Even in the near-perfect vacuum of interstellar space, there are stray atoms and molecules. Perhaps this white dwarf is moving through a slightly denser cloud, gathering this tenuous gas at a very slow, steady rate. As this material plummets onto the star's surface, it would compress and heat violently, producing the observed X-ray glow. It would be a cosmic candle feeding on the faintest of breezes. A second theory is more dramatic. It suggests the star is not just hot on the surface, but actively burning fuel. A thin layer of hydrogen, perhaps leftover from its formation or gathered later, could be undergoing steady, low-level nuclear fusion on the white dwarf's crust. This would act as a natural furnace, maintaining the incredible temperature against the relentless pull of cooling. The most spectacular explanation, however, is a cataclysm in the recent past. This white dwarf might be the product of a merger, the violent collision and blending of two smaller white dwarfs that occurred perhaps only a few thousand years ago. Such an event would inject a tremendous amount of fresh thermal energy into the newly formed object, reheating its core to white-hot levels and explaining its youthful glow. Each theory has its own challenges. The accretion rate needed is so low it borders on the imperceptible. The nuclear burning model requires a very specific and delicate balance of conditions, and a merger event, while powerful, should leave other observational clues that have not yet been found. KPD 0005 plus 5106 remains a solitary question mark, a radiant enigma proving that even a star dying alone can hold onto secrets of fire and rebirth. The searing glare of a lone, hot star gives way to a subtler, more common signal, a whisper of warmth that has become a cornerstone of white dwarf mysteries. Our 7th and 8th signals come from the pair GD362 and GD56, two stellar graveyards that share a haunting signature but guard their own unique secrets. The shared signal is an infrared excess, a persistent glow of heat beyond what the white dwarf itself should produce. This is the unmistakable fingerprint of circumstellar dust, vast rings or disks of fine, rocky debris orbiting these dead stars. In both cases, this dust is the ground-up remains of planetary bodies, asteroids or perhaps even small planets that wandered too close and were torn apart by gravity. These are not active demolition sites like our earlier examples, but quieter, more settled crime scenes, the dust having settled into stable orbits. Yet within this apparent calm, deep incongruities emerge. For GD362, the dust itself tells a bizarre story. When astronomers analyzed its composition through spectroscopy, they found it was not just simple rock. The debris was incredibly rich in lithophilic elements, the building blocks of planetary crusts, but it also carried the spectral signature of water ice. This combination is profoundly strange. In the scorching vicinity of a white dwarf, any ice should have sublimated into vapor almost instantly. Its presence suggests the destroyed body was not a simple asteroid, but a large, differentiated object, one that had separated into a core, mantle, and crust through internal heating long ago. The best explanation is that GD362 consumed something akin to Ceres in our own solar system, a protoplanet or large asteroid with a water-rich crust and a rocky interior. The mystery is how that icy material survived the star's red giant phase when it would have been engulfed in a stellar furnace, or how it was delivered so recently that the ice has not yet vanished. We are looking at the ghost of a small, watery world, a relic from a planetary system that somehow preserved its volatile treasures only to have them scattered as dust around a dead sun. GD56 presents a different kind of puzzle, one of motion and change. Its dust disk is not a placid, uniform ring. Instead, its infrared brightness fluctuates over time in a jagged, unpredictable pattern. This variability is the signal of a disk in turmoil. The changes are not smooth, suggesting the debris is not evenly distributed. Instead, the disk is likely clumpy, with dense knots and sparse voids of material orbiting the star. These clumps could be the remnants of recent, violent collisions within the disk itself, as larger fragments continue to pulverize each other, or they might point to the gravitational influence of a surviving, unseen planet, its pull shepherding the dust into concentrated arcs and bands that rotate in and out of our view, causing the brightness to rise and fall. Each flicker in the infrared glow is a snapshot of an unstable system, a graveyard where the dust has not yet settled into a final, quiet configuration. Together, GD362 and GD56 show us that even the classic signpost of planetary destruction, the dusty disk, is not a simple phenomenon. One holds the frozen memory of a lost ocean, while the other thrums with the chaotic aftermath of an unfinished demolition. Some white dwarfs do not just possess magnetic fields, they wield them as cosmic weapons. Our ninth signal comes from the stellar corpse known as ReJ0317-853, and its broadcast is one of pure, distorted force. This signal is not a flicker or a pulse of light, but a fundamental alteration of the light itself. When astronomers analyze this star, they find its light waves are not scattered randomly, but are strongly polarized, forced to vibrate in a single plane by an unimaginably powerful magnetic field. Furthermore, the chemical fingerprints in its spectrum are not sharp lines, but broad, smeared bands, as if the very atoms on its surface are being stretched and twisted by magnetic forces billions of times stronger than Earth's own field. This is not a gentle pull, it is a fundamental reshaping of the local universe. Such a field acts as an impenetrable shield, a colossal force field that dictates reality in the space around the star. Any material, like dust or gas from a shredded planet, does not simply fall onto the surface. Instead, it is funneled violently toward the magnetic poles, slamming into the star in concentrated, ultra-hot columns that can create unique and brilliant emission signatures like cosmic searchlights. The profound mystery, however, is where this monster of magnetism came from. There are two competing cosmic origin stories. The first suggests it is an inherited trait, that the progenitor star which collapsed to form this white dwarf was itself a magnetic giant, and that field was simply compressed and amplified during the star's death throes, frozen into the dense remnant like a fossil. The second, more violent theory posits that the field was generated during the collapse itself, as the star's core dynamo was squeezed and spun up, creating a magnetic dynamo of unprecedented power in its final moments. The plot thickens with the star's rapid spin. ReJ0317-853 rotates at a breakneck pace, completing a full turn in just minutes. This ferocious spin is a classic clue pointing to a past merger, the collision and blending of two white dwarfs that would have transferred immense rotational energy to the new object. Did that catastrophic merger also trigger or amplify the magnetic field? Or is the spin a separate chapter in this star's violent biography? The signal from this magnetic monster is clear, but the story it tells is written in a language of forces we are still learning to read, a testament to the universe's ability to forge engines of pure power in the graves of dead suns. The universe holds clocks of chaos as well as order. The 10th signal is a flickering, stuttering shadow cast by the white dwarf WD10542226, and its light curve is one of the most bizarre patterns ever recorded. Every 25 hours, like a broken metronome, this star's brightness begins to dip, but the rhythm is not clean. Instead of a single, smooth eclipse, the light drops in a frantic, unpredictable dance. Clusters of dimming events pile upon one another, some shallow, some deep, lasting for minutes before the star regains its normal glow, only to begin the chaotic performance again roughly a day later. This is not the signal of a single solid object, but of something fluid, shifting, and alive with motion. The leading hypothesis paints a picture of cosmic pandemonium. Orbiting the white dwarf is not one object, but a vast, roiling swarm of dusty debris clouds. These are not neat rings, but irregular, evolving clumps of pulverized rock and dust, each casting its own jagged shadow as it passes between the star and our telescopes. The sheer complexity of the pattern suggests these clouds are not stable. They are constantly forming, perhaps through collisions, and then breaking apart, their shapes and orbits shifting in real time. This presents a dynamic puzzle of orbital mechanics that utterly defies simple modeling. The most compelling clue to this chaos is the 25-hour period itself. Such a precise anchor amidst the turmoil strongly hints at a hidden architect, an unseen planet orbiting just beyond the debris. Its steady gravitational pull could act as a shepherd, confining the dusty clouds within a specific orbital zone and creating a resonant pattern that repeats daily, even as the individual clouds within that zone collide and swirl in unpredictable ways. Yet the irregularity remains the profound mystery. If a planet is shepherding the debris, why is the resulting shadow play so wildly inconsistent? It suggests the system is in a state of violent flux, where the forces of gravity, radiation, and collision are locked in a battle with no stable outcome. We are not looking at a finished graveyard, but at a demolition site where the wrecking ball is still swinging, where piles of rubble are being bulldozed into new shapes before our eyes. The flickering light of WD10542226 is a live broadcast of orbital anarchy, a reminder that even around a dead star, the universe is never truly still. This chaos of dust and shadow finds its ultimate expression in a star that did not stay to clean up the mess. The 11th signal is one of pure, unbridled motion, a streak of light hurtling across the galaxy. The white dwarf known as LP40-365 is not just moving quickly, it is a runaway, a cosmic bullet traveling at over 2 million miles per hour. Its signal is written in two parts, its blistering trajectory and the bizarre chemical fingerprint it leaves in its wake. When astronomers captured its spectrum, they expected the usual hydrogen or helium. Instead, they found a stark, almost pure atmosphere of neon, oxygen, and magnesium. These are not the building blocks of a normal star, they are the ashes of a stellar furnace. This is the debris from partial thermonuclear fusion, the kind of violent nuclear burning that happens during a supernova. The conclusion is as dramatic as it gets. LP40-365 is not merely a white dwarf, it is a survivor, a shrapnel fragment blasted away from a cataclysm. The prevailing theory is that this star is a piece of a type IX supernova, often called a zombie star event. In this scenario, a white dwarf in a binary system siphoned too much material from its companion, reigniting fusion on its surface. But instead of a full, total detonation that would vaporize the star completely, the explosion was lopsided and failed. It blew the star apart just enough to eject this bizarre, fused chunk into the void while leaving a damaged remnant behind. This runaway shard is the evidence. Yet the precise mechanics of its escape remain a haunting puzzle. What was the nature of its binary partner that fed it to the brink of destruction? Was it another white dwarf or a more typical star? More critically, what was the exact sequence of forces inside that failed explosion? To be shot out at such an incredible velocity, the ejection had to be phenomenally precise, a cosmic cannon firing a stellar fragment with just the right amount of force to propel it without completely disintegrating it. The survival of LP40-365 in this recognizable, coherent form is a fluke that challenges our models of stellar death. It is a ghost ship sailing the void with the unmistakable scorch marks of a fire that should have consumed it entirely, carrying the secret of its own miraculous escape locked within its strange, metallic heart. The runaway survivor proves that white dwarfs can be forged in violent, partial explosions. Our 12th signal presents a different kind of internal upheaval, one that rings like a bell and glows with the wrong kind of ash. The white dwarf WDJ0914+1914 broadcasts a dual mystery in perfect harmony. Its light does not simply shine, it breathes. The star pulses, expanding and contracting with a steady, predictable rhythm, causing its brightness to rise and fall every few minutes. These are not random flickers, but coherent oscillations, the resonant vibrations of the entire stellar body. For astronomers, this is a gift. Just as seismologists use earthquake waves to map Earth's hidden layers, they can use these stellar pulsations to probe the deep interior of this dead star. The vibrations reveal the density, composition, and even the temperature structure buried beneath the surface, offering an ultrasound of a stellar corpse. Yet the image that emerges is profoundly strange. The star's spectrum, its chemical fingerprint, is dominated by one element, carbon. Its atmosphere is a blanket of soot, with almost no trace of the hydrogen or helium that cloak nearly all other white dwarfs. This is the core of the enigma. In a typical star's death, the lighter elements form the outer layers, while the products of fusion, like carbon and oxygen, sink to form the dense core. Here, that order has been violently inverted. The carbon from the core has somehow risen to the surface, while the star's original outer envelope has vanished. The pulsations provide clues to this geological upheaval. The specific modes and frequencies of the vibrations suggest the star has a very thin surface layer, if any, covering a dense, crystallizing interior of carbon and oxygen. It is as if the entire outer skin of the star has been peeled away. So what cosmic surgeon performed this operation? One leading theory points to a vampiric companion. Perhaps this white dwarf once orbited a nearby star, and through a complex gravitational dance, it had its hydrogen and helium envelope completely stripped away, ripped off to leave the bare, carbon-rich core exposed to space. Another, more internal explanation is a late thermal pulse. This is a final, dying gasp of nuclear fusion that can occur in the star's twilight, a belated burst of energy that violently convulses the star, mixing its interior and dredging core material up to the surface in a process called a dredge-up. The pulsations themselves may be a direct result of this traumatic mixing, the star ringing from the internal shock. The data from the quakes leans toward a specific history, but a definitive verdict remains elusive. Is WDJ0914 plus 1914 the victim of stellar theft, or did it purge its own atmosphere in a final fiery fever? Its rhythmic light holds the answer, a slow, steady heartbeat from a star that turned itself inside out. A clear, rhythmic shadow is the 13th signal, a whisper of survival from the white dwarf WD1856 plus 534. For years, astronomers had catalogued thousands of planets orbiting living stars, but the fate of those worlds when their suns died was pure speculation. Then this star delivered an answer. The signal was textbook perfect, a clean, periodic dip in brightness occurring every 1.4 days. A Jupiter-sized object was passing directly in front of the stellar corpse, blocking a fraction of its light in a flawless, repeating transit. This was not debris or dust, but the silhouette of a whole, intact giant planet. The discovery was monumental, proving conclusively that massive planets can endure the apocalyptic violence of their star's red giant phase. They are not always consumed. They can witness the death of their sun and live on to orbit its ghost. Yet the planet's very existence in its current orbit is a paradox that unravels any simple story of survival. This gas giant orbits staggeringly close to the white dwarf, completing a full revolution in just 34 hours. At that distance during the star's red giant phase, it would have been deep inside the star's swollen, tenuous outer layers, utterly engulfed in a stellar furnace for millions of years. Any planet submerged like that should have been vaporized by friction or dragged down to a fiery death. So how did it get to this impossible address? The transit signal is clear, but the planet's journey is a dynamical nightmare to reconstruct. Astronomers are piecing together a history of gravitational chaos. One leading theory suggests the planet was not always this close. It may have originally orbited much farther out, a distant sentinel watching its star expand. Then, as the star lost mass and shrank back into a white dwarf, the gravitational landscape of the entire system shifted violently. The delicate balance holding the planets in place was broken. In the ensuing instability, this giant world could have been scattered inward by gravitational kicks from other surviving planets, like a cosmic billiard ball sent on a new, perilous trajectory that eventually circularized right at the star's doorstep. A gentler but no less complex possibility is smooth migration. Perhaps the planet's orbit slowly decayed over billions of years due to subtle tidal forces from the white dwarf, a gradual, spiraling dance that brought it safely inward long after the red giant's fire had subsided. This requires a very specific set of conditions, a system calm enough for such a slow, graceful waltz to occur without further disruptive encounters. The most dramatic scenario paints a picture of a system in utter turmoil. The current close orbit might be the final, quiet chapter of a story involving multiple giant planets. Their gravitational tug of war could have ejected some worlds entirely into interstellar space, while flinging this one into its tight, scorching embrace with the dead star. The clean transit we see today would then be the calm after a storm of celestial violence, the last planet standing in a rearranged graveyard of worlds. Each explanation demands a different history, a hidden narrative of pushes and pulls that we must infer from a single, quiet shadow. The giant planet of WD 1856+534 is both a testament to endurance and a profound cipher, its present position a clue to a past filled with chaos we can only begin to imagine. After the violent chaos of surviving giants, we find a star that has achieved the ultimate peace. The 14th signal is a whisper of cold, a profound silence from a white dwarf designated PSOJ 174.5335-10.2046. Its signal is not a pulse or a flare, but an absence, a profound and deepening chill. This stellar corpse is so ancient, so utterly spent of its thermal energy, that it has faded to a dim, infrared ember barely warmer than the background of space itself. It belongs to a class known as ultra-cool white dwarfs, relics so old they may predate the very disk of our galaxy, making them among the first generation of stars to die. Their faint glow is a fossilized echo from the universe's youth. Yet within this deep freeze lies a quantum transformation of staggering scale. The leading theory is that the interior of this white dwarf is no longer a hot fluid, but is undergoing a slow, magnificent phase change. As it cools past a critical threshold, the super-dense soup of carbon and oxygen in its core is predicted to begin solidifying, not into a brittle solid, but into a crystalline lattice. Imagine a diamond the size of a planet, its atomic structure ordered into a perfect, repeating pattern by the immense pressures at the star's heart. This is not science fiction. It is a direct prediction of quantum mechanics applied to stellar corpses. The mystery, however, is how to confirm this state from thousands of light years away. We cannot see inside the star. Instead, astronomers look for a subtle clue in the cooling curve, a graph that plots a white dwarf's temperature against its age. For ultra-cool dwarfs like PSOJ 174.5335-10.2046, something peculiar happens. Their observed temperatures appear to stall or pile up, making them seem cooler than standard cooling models predict for their estimated age. This discrepancy is the key signature. One compelling explanation is the release of latent heat. When a substance crystallizes like water freezing into ice, it releases energy even as its temperature remains constant. If the white dwarf's core is crystallizing, that process would inject a fresh pulse of heat into the star, slowing its visible cooling for perhaps 1 billion years and creating that pile up on the graph. It would be a final, slow sigh from a solidifying heart, but there is a competing, equally profound possibility known as phase separation. As the core cools, the dense mixture of carbon and oxygen may not freeze uniformly. Instead, the oxygen, being slightly heavier, could sink downward like a slow-motion rain while the carbon rises. This gravitational sorting releases its own gravitational energy, which also acts as a heat source, delaying the star's fade to black. Distinguishing between these two processes, crystallization versus elemental rain, is an immense challenge. Both would produce a similar observational signal, a prolonged twilight. This ultra-cool enigma is more than a curiosity about old stars. It is a direct probe into quantum mechanics and material science operating on a scale we can never replicate. The faint infrared glow from this ancient crystal sphere carries encoded within it the secrets of how matter behaves under the most extreme confinement. A final, slow message from a star that has become something entirely new. The serene chill of a crystallizing star gives way to a far more complex architecture of ruin. Our 15th signal comes from the white dwarf SDSS-J 1557+0916, and its message is written not in a single glow, but in a layered whisper of heat. The signal itself is a complex infrared spectrum, a detailed breakdown of the warmth radiating from around the star. When astronomers analyzed this data, they found it was impossible to explain with just one source. The pattern of wavelengths demanded two distinct temperatures, a searing inner band and a much cooler outer region. This is the signature of a double-decker disk, a celestial structure with two separate, concentric rings of debris orbiting the dead star at vastly different distances. It is not a single, messy graveyard, but a carefully zoned demolition site. The hot inner ring likely consists of fine dust and vaporized rock skimming perilously close to the white dwarf's scorching surface, a place where any solid material would be constantly on the verge of sublimating into gas. The cooler outer ring is farther out, a more sedate collection of coarser, rocky fragments that have settled into a wider, more stable orbit. This arrangement paints a vivid picture of a planetary system that did not die all at once. Perhaps we are seeing the remains of multiple destroyed bodies, a rocky inner planet and a more distant icy asteroid belt, each ground to dust at different times. Or, more intriguingly, this could be the stratified remains of a single giant world, a body so large that when it was torn apart, its material sorted itself by composition and density, with heavier metals falling inward and lighter silicates spreading outward, creating these distinct rings. The profound mystery is not the debris itself, but the invisible architecture that maintains this clean separation. In our own solar system, the sharp edges of Saturn's rings are maintained by the gravitational influence of tiny shepherd moons. By analogy, the most elegant explanation for this double-decker disk is the presence of one or more surviving planets acting as cosmic traffic cops. Their steady gravitational pull would carve gaps in the debris and confine the dust into these two neat, distinct bands, preventing the material from mixing into a single, featureless cloud. Yet, as with so many of these mysteries, no such shepherd planet has been found. Its absence forces us to consider more exotic possibilities. Could the two rings be made of fundamentally different stuff? If the inner ring is rich in iron and other metals that condense at high temperatures, and the outer ring is silicate-rich, their different responses to the star's radiation pressure might naturally keep them apart. Or perhaps we are witnessing a temporary, fleeting state. The system might be caught in a moment of dynamical transition, where a recent, violent collision has ejected debris into both close and far orbits, and the architecture we see is simply the chaos before everything eventually settles or falls in. The layered infrared glow from SDSS-J 1557+0916 is a snapshot of organized destruction, a hint that even in death, a planetary system can retain a ghostly echo of its original complex structure, maintained by forces we have yet to fully see. HZ21 is a star that has been stripped to its barest essence. Our 16th signal is a spectrum of startling purity, a chemical fingerprint showing an atmosphere composed almost entirely of helium. This is a profound anomaly, Over 95% of all white dwarfs cloak themselves in hydrogen, the universe's most abundant element left over from their birth. A helium-dominated atmosphere is a rare and telling deviation, the sign of a profound cosmic stripping. The signal is clear, but the story it tells is one of violent loss. Somehow, this star was completely denuded of its primordial hydrogen blanket. The question is what cosmic barber performed this extreme shave and when. The first possibility is a sustained, ferocious wind. In the late stages of its life, as the star swelled into a red giant, it might have experienced a period of exceptionally powerful stellar winds. These outflows, driven by pulsations and intense radiation, could have blown away the entire hydrogen envelope, leaving the underlying helium layer exposed as the star collapsed into its white dwarf state. It would be a slow, steady erosion over millennia. A second, more interactive scenario involves theft. HZ21 may once have been part of a binary system. Its outer hydrogen layers could have been gradually siphoned off by a greedy companion star, transferred through a stream of gas until nothing but helium remained. The twist is that this companion, having feasted, might have then been lost, ejected from the system by gravitational interactions or consumed in the chaos of the star's death throes, leaving HZ21 as a solitary monument to stellar cannibalism. The most dramatic origin story, however, is one of collision and fusion. This white dwarf might not be the descendant of a single star at all, but the merged product of two helium-core white dwarfs that spiraled together and coalesced. Such a violent union would naturally produce a remnant with a helium-rich composition, its hydrogen long since burned away or ejected in the merger cataclysm. Each of these histories leaves a different set of clues in the star's present state: its precise surface temperature, its gravity, its motion through space. Astronomers use these measurements like forensic evidence, comparing them to models of each scenario. The data provides constraints but not yet a verdict. The helium purity of HZ21 is a lasting clue, a stark signature of a past so dramatic it erased the star's original identity. We are left with the elemental core of a mystery, a star that stands as a ghost of either a great escape, a great theft, or a great collision. The stark purity of a helium atmosphere gives way to a system of perfect, decaying symmetry. The 17th signal is not a flash of light or a whisper of heat, but a relentless countdown. It emanates from the binary white dwarf system as DSSJ 0651 plus 2844, a pair of stellar corpses locked in the tightest gravitational embrace ever discovered. Their orbital dance is breathtakingly fast, a full revolution completed in just 12.75 minutes. In the time it takes to listen to a single song, these two Earth-sized remnants circle each other entirely. The signal we observe is the precise timing of their eclipses as one star passes in front of the other, blocking its light with the regularity of a cosmic stopwatch. But this clock is running fast. Each orbit takes a tiny, measurable fraction of a second less than the one before. This is the smoking gun of gravitational waves, ripples in the fabric of space-time itself. As the two massive stars whirl around each other, they churn the fabric of the universe, sending out waves of pure gravity that carry energy away. That lost energy pulls the stars closer together, tightening their orbit and speeding up their dance in a slow, inevitable spiral toward merger. The eclipse timings from this system provide the most exquisite, real-world confirmation of this prediction from Einstein's theory, a direct observation of orbital decay driven by gravitational radiation. Yet within this triumph of confirmation lies a subtle, nagging whisper of discord. The orbital period is shrinking, just as relativity demands. But when astronomers plot the exact moments of each eclipse against the perfect, smooth curve predicted by a simple two-body gravitational wave model, the data points do not land perfectly on the line. They show tiny, persistent deviations, timing residuals that are just a fraction of a second off. these minuscule hiccups in the countdown are the true mystery. They mean something else. Some additional force is ever so gently tugging on the dancers, throwing their perfect rhythm out of sync. One compelling possibility lies within the stars themselves. As they draw closer, their immense gravitational pulls stretch and distort each other, creating tidal bulges. The flexing of these ultra-dense bodies dissipates energy in a different way, which could alter the spiral in a manner not fully captured by our models. It is the internal groaning of dead stars under terrible stress. A second, tantalizing idea points to a hidden audience for this dance. A distant, low-mass third object, like a planet or a brown dwarf, could be orbiting the pair. Its gentle, persistent gravitational nudge would subtly perturb the binary's center of mass, causing the eclipses to arrive slightly early or late in a pattern we could eventually decode. After years of searching, no such companion has been found, making its potential presence a ghost in the orbital machinery. The most profound possibility, however, touches the foundations of physics itself. Could these tiny timing residuals be a hint that our theory of gravity, while spectacularly successful, requires a minute adjustment in such an extreme environment? This binary is a natural laboratory of staggering precision, testing the laws of the universe under conditions of immense gravity and velocity that we can never recreate on Earth. Any deviation from prediction is a potential window into new physics. The steady, quickening heartbeat of SDSS J0651 plus 2844 is more than a celestial curiosity. It is a metronome counting down to a deeper understanding of how space, time, and mass intertwine. Each tick brings these stellar ghosts closer to a final collision, and each tiny, unexplained tock asks us if we fully understand the rules of their disappearance. The clean, predictable decay of a binary clockwork is replaced by a signal of distant, frozen memory. Our 18th mystery emanates from the white dwarf LHS 1038, and its secret is written not in metal but in gas. The signal is a set of strong, dark absorption lines in the star's spectrum, the unmistakable fingerprint of nitrogen. This discovery is far stranger than it might sound. While finding heavy metals like iron or calcium polluting a white dwarf's atmosphere is common, the sign of shredded rocky worlds, nitrogen is a different beast entirely. It is a volatile element, one that exists as a gas or ice at relatively low temperatures. Its presence here is a profound clue about the type of world that met its end. Nitrogen, especially in the form of ammonia ice, is a classic building block of the outer solar system, the stuff of comets and icy dwarf planets in places like our own Kuiper belt. The unavoidable conclusion is that LHS 1038 is not consuming the remains of a rocky planet like Earth, but is instead feasting on the scattered debris of a distant, frozen body. We are seeing the ghost of a comet or a small, icy world, now vaporized into a tenuous cloud of nitrogen gas around the dead star. This paints a breathtaking picture of the star's original planetary system. It must have been vast and structured, with distinct zones just like our solar system, containing both inner rocky planets and a distant reservoir of icy objects far beyond the snow line. The deep mystery, however, is one of delivery. How did this frozen relic from the system's outermost fringe end up on a suicidal plunge into the star's atmosphere billions of years after the star itself died? An object from such a distant, stable orbit should have remained peacefully in the deep freeze, untouched by the star's violent red giant phase. Its arrival now implies a late, dramatic rearrangement. The most likely explanation involves a gravitational puppet master, a surviving giant planet orbiting between the white dwarf and the distant icy belt could have acted as a gravitational slingshot. Over eons, its steady pull might have gradually perturbed the orbit of one of these frozen objects, nudging it onto a wildly elliptical path that eventually brings it skimming catastrophically close to the white dwarf. Another possibility is a more recent violent event. Perhaps two icy bodies in the distant belt collided, sending shrapnel inward, or the gravitational influence of a passing star long ago stirred up the entire reservoir, initiating a slow rain of comets that is only now reaching the star. The nitrogen in the atmosphere of LHS 1038 is more than a pollutant. It is a message in a bottle from the frozen frontier of a lost solar system, telling us that even the most distant and ancient objects are not safe from the gravitational turmoil that follows a star's death. From the frozen nitrogen of a distant ice belt, we arrive at a system that is very much alive with furious energy. The 19th signal is a cosmic lighthouse, a relentless beacon that pulses across the entire electromagnetic spectrum. It originates not from a solitary star, but from the binary dance of Astronomers, a pair where a white dwarf and a red dwarf are locked in a devastating embrace. Every 1.97 minutes, like clockwork, the entire system erupts in a brilliant flash of light, from visible optical waves to ultraviolet and even radio. This is not the gentle heartbeat of a pulsating variable star. It is a sledgehammer blow of radiation repeated with metronomic precision. The source of this power is the white dwarf, but its target is its companion. This stellar corpse possesses a magnetic field of almost unimaginable strength, billions of times more powerful than Earth's. This field acts as a natural particle accelerator, a cosmic slingshot that whips electrons to velocities approaching the speed of light. These ultra-relativistic particles are then blasted outward, not into empty space, but directly into the atmosphere of the hapless red dwarf companion. The result is a continuous, violent bombardment. Each pulse we see is the moment that focused beam of high-energy particles slams into the face of the red dwarf, heating its surface to incandescence and forcing it to shine with a light not its own. The red dwarf is essentially being used as a cosmic phosphor screen, lighting up under the relentless particle gun of its dead partner. The signal is clear, but the engine driving it remains a profound puzzle. The exact mechanism of this particle acceleration is a subject of intense debate. One model describes the system as a unipolar inductor, where the white dwarf's magnetic field, sweeping through the conducting plasma of the red dwarf's atmosphere, generates a colossal electrical voltage that then accelerates the particles. Another theory posits a magnetic propeller, where the white dwarf's rapid spin and immense field fling material off its own surface and channel it into the devastating beam. Or perhaps it is a hybrid process, a complex interplay of magnetic fields and plasma flows we have yet to fully map. Adding to the complexity is the system's long-term behavior. While the 1.97-minute pulse is unwavering, the overall brightness of Astronomers waxes and wanes over months and years. This suggests the bombardment is not constant in its intensity, that the flow of particles or the response of the red dwarf's atmosphere changes over time. Is the white dwarf's rotational energy slowly depleting? Is the red dwarf's atmosphere being stripped away or altered by the endless assault, changing how it glows when struck? This longer-term variability is a second, slower rhythm in the symphony of violence, a clue that even this seemingly stable engine of destruction is evolving. Astronomers is a unique laboratory of extreme physics, a place where a dead star's magnetic fury is written in light across the face of a living one, and where every precise, brilliant pulse asks us how such a terrible and beautiful machine truly operates. The furious, visible violence of a particle beam gives way to a mystery written not in light but in absence. Across the galaxy, when astronomers catalogue thousands of white dwarfs and sort them by temperature and composition, a strange, silent signal emerges from the data. There is a conspicuous and puzzling gap in the population. Among white dwarfs with pure helium atmospheres, there is a distinct lack of stars with surface temperatures between roughly 30,000 and 45,000 degrees Celsius. This missing population is known as the DB gap, and its existence is a profound clue about the final, quiet transformations of dying stars. The signal is not a flash or a pulse from any one star, but a statistical ghost, an empty chair at the cosmic table where a whole class of objects should be sitting. It tells us that something universal and inevitable happens to these stars as they cool through this specific fiery range. The leading theory to explain this gap is a story of atmospheric upheaval, a slow motion overturning within the star itself. Picture a white dwarf with a helium atmosphere cooling down from a searing birth. As its temperature drops into this critical 30 to 45,000 degree range, the physics of its outer layers undergoes a dramatic shift. The helium gas under these conditions becomes violently convective. It begins to boil and churn like a pot of water on a high flame. This turbulent motion digs deep, and if there is even a whisper-thin layer of hydrogen buried beneath the helium, left over from the star's earlier life, the churning will dredge it up. Hydrogen, being the lightest element, then floats to the surface like cream rising in milk. This process fundamentally changes the star's identity. To our telescopes, it is no longer a helium atmosphere to be white dwarf. It has been reclassified as a hydrogen atmosphere DA star. The DB gap, therefore, is not a graveyard but a transformation hallway. Stars enter it as one type and exit it as another. Yet this elegant explanation is haunted by a persistent discrepancy. While the basic picture of convective mixing is sound, our most detailed computer models of stellar atmospheres struggle to replicate the exact, sharp boundaries of the gap observed in nature. The transition temperatures predicted by theory do not line up perfectly with the clean edges seen in the actual census of stars. This mismatch is the core of the ongoing mystery. It suggests that our understanding of the physics in these extreme environments, the precise way energy transports through a dense, degenerate plasma under immense gravity, is still incomplete. Some subtle ingredient is missing from our equations. Perhaps it involves the intricate interplay of trace elements like carbon or oxygen, which can act as catalysts or inhibitors in the mixing process. Or maybe it relates to the strength and structure of the star's magnetic field, which can suppress convection and alter the timing of the hydrogen dredge up. The DB gap is a silent majority signal, a blank space on a graph that speaks volumes about the hidden, uniform processes that govern the slow fade of stellar embers, reminding us that even in the quietest phases of cosmic death, the details still defy us. The 20th signal was a cosmic outburst witnessed in real time. The white dwarf WD0145 plus 234 had been a quiet, unremarkable point of light for years. Then, in 2018, its infrared signature suddenly flared to over 10 times its normal brightness. This was not a slow change, but a dramatic spike, a brilliant pulse of heat appearing around the dead star as if someone had thrown a switch. The signal was the unmistakable glow of warm dust, a vast amount of it, materializing almost instantly in the star's vicinity. This was not the steady rain of debris from a disintegrating planet, but something far more explosive. The leading explanation paints a picture of staggering violence in the cold outer darkness. Astronomers believe we witnessed the aftermath of a cataclysmic collision between two massive bodies in the star's distant reaches, perhaps two large asteroids or even dwarf planets. The impact would have been apocalyptic, pulverizing both objects into a colossal, expanding cloud of fine dust and rubble. This immense shroud of debris then began a slow drift inward, its particles spreading out and warming as they approached the star's radiation, creating that brilliant, temporary infrared flare. The sheer scale of the event is the first great mystery. To produce such a dramatic infrared signature, the colliding bodies had to be substantial, possibly hundreds of miles across. This implies that the white dwarf's planetary system, long after the star's death, still harbored significant, intact worlds in its frozen outer belt. Their very existence so late in the system's history is a surprise, but the deeper, more unsettling question is the trigger. What could possibly cause two such large, stable objects to collide billions of years after their star has died, and the system should have settled into a quiet, predictable rhythm? In a calm system, orbits are stable, and collisions of this magnitude are astronomically rare. Something must have violently disturbed the delicate gravitational balance. The perturbation needed is profound. It could be the gravitational hand of an unseen giant planet, its slow, persistent tug finally destabilizing the orbits of these distant relics after eons. Or perhaps it was a more recent and chaotic event, like a close stellar flyby from a passing star that rattled the entire outer system like a pebble in a tin can, sending its inhabitants on new, deadly trajectories. The most extreme possibility is that we are seeing the end game of a long, slow orbital resonance, a gravitational drumbeat that took billions of years to finally build to a crescendo of destruction. The transient infrared flare from WD0145+234 is a flashbulb illuminating a single moment of chaos in an otherwise dark and silent graveyard. It proves that planetary systems around dead stars are not static museums, but can remain dynamically active, even violently so, for timescales that dwarf human history. The dust has now faded, but the question remains hanging in the void. What unseen clockwork ticking for eons finally struck the hour of demolition? The atmosphere of a dead star can hold the chemical ghost of an entire world. Our 20-second signal comes from the white dwarf SDSS J1043+0855, and its spectrum is a detailed forensic report from a planetary murder scene. The light from this star is not pure. It is stained with the unmistakable fingerprints of heavy elements, but this is no simple pollution. The precise cocktail of elements tells a specific and breathtaking story. Lithium, sodium, potassium, and calcium appear in ratios that do not match the bulk composition of a simple asteroid or a primitive, undifferentiated ball of rock. Instead, they align almost perfectly with the material that makes up the continental crust of our own planet Earth. This is the signal, a chemical echo of a shattered crust. The conclusion is profound. The white dwarf is not accreting just any rocky debris. It is consuming the ground-up remains of a planet that had a complex, layered interior, a world that underwent the process of planetary differentiation. This means, long ago, the parent body was hot enough and massive enough for its interior to melt, allowing heavy metals like iron to sink to form a core, while lighter, silicate-rich materials rose to form a mantle and, crucially, a distinct, evolved crust. We are witnessing the aftermath of the destruction of a body that was geologically akin to Earth or Venus. This allows astronomers to perform remote planetary geology on a world that no longer exists. By reading the ratios in the stellar atmosphere, we can infer the type of rock that was destroyed. The abundance of lithophilic or rock-loving elements points to a crust that was not just basaltic, like the ocean floors of Earth, but more granitic, like our continents. This hints at a further, even more remarkable possibility. The formation of such silica-rich, evolved crusts on Earth is driven by the relentless engine of plate tectonics, where crust is recycled into the mantle and remelted, creating new, complex rock types. The signature in SDSS J1043+0855 suggests the destroyed planet may have had its own version of this dynamic geological process. It may have had continents, mountain-building events, and perhaps even a geologically active past that shaped its surface over billions of years before its star died. This transforms the mystery from a simple question of destruction to a deeper inquiry about cosmic rarity and evolution. We know Earth-like planets exist, but how common are they around other stars? And more specifically, how many of those Earth-like worlds develop the complex geological machinery to create continental crust? This single spectrum suggests such worlds are not only possible, but that their remains can survive the apocalypse of their sun's death and deliver their final testimony to us. The white dwarf's atmosphere becomes a cosmic archive, holding the last chemical record of a lost world's mountains, plains, and perhaps even the very ground that might have, under different circumstances, cradled an ocean or a range of alien peaks. The ultimate cosmic escape artist is a streak of light named SDSSJ1238+1946. This white dwarf is a runaway of the highest order, a stellar corpse hurtling through the galaxy at a staggering speed. Its signal is twofold: its blistering velocity and, more tellingly, the path it has carved across the sky. When astronomers traced its trajectory backward, they found it did not originate in the familiar spiral arms of the galactic disk. Instead, its path points like an arrow to a far more exotic birthplace, likely a densely packed globular cluster orbiting the Milky Way, or perhaps even a small satellite galaxy that was cannibalized eons ago. This is not a local fugitive, it is an immigrant from a different stellar neighborhood entirely. To achieve such a velocity and such a distant origin requires a launch mechanism of almost unimaginable power. In the crowded core of a globular cluster, stars engage in a relentless gravitational dance. A close encounter between two binary star systems could act as a natural slingshot, flinging one of the stars, like this white dwarf, out of the cluster entirely at tremendous speed. It would be a gravitational billiard shot on a cosmic scale. An even more violent possibility involves a binary partner that met a cataclysmic end. If this white dwarf was once paired with a massive star that exploded as a supernova, the asymmetric detonation could have kicked the surviving companion away like a stone from a sling, sending it on an interstellar journey. The most extreme launchpad of all would be the vicinity of a supermassive black hole, where the mind-bending physics of a three-body interaction could literally punt a star out of its home galaxy. The specific, haunting mystery of SDSSJ1238+1946 is the identity of its true homeland. Pinpointing whether it came from a specific globular cluster or from the ghostly stream of a devoured dwarf galaxy would transform this lone traveler into a scientific probe. Its chemical composition, a fossil record of its formation environment, could tell us about the unique stellar populations in those dense, ancient places. It could reveal whether stars from such environments have distinct elemental signatures compared to stars born in the galactic disk. Even more remarkably, if its path definitively leads beyond the Milky Way's gravitational grasp, it would become a rare example of an intergalactic traveler, a test particle for the idea that stars can be exchanged between galaxies during close encounters or mergers. This unbound rogue is more than just a fast-moving star. It is a signal in motion, a messenger carrying encoded information about the violent dynamics of the universe's most crowded places and the possibility of stellar migration across the vast, empty gulf between galaxies. Low-mass white dwarfs are the cosmic runts of the litter stellar remnants that never grew to their full potential. Our 24th signal comes from the star NLTT 11748, a white dwarf locked in a tight binary dance, and its most telling feature is what is missing. This stellar corpse possesses a mass of only about 1/5 of our Sun, a fraction of what a typical white dwarf should be. That profound lack of mass is the primary signal, a screaming clue to a violent past. A star this lightweight could not have forged an iron core and died the usual way. Instead, it is the exposed helium core of a star whose life was cut brutally short. The favored story is one of stellar theft and cosmic chaos. Long ago, this star likely had a companion in a close orbit. As it aged and began to swell, the two stars spiraled into a shared atmospheric embrace, a phase called a common envelope. In this stellar fog, friction robbed the dying star of its entire hydrogen-rich outer layers, stripping it down to its bare helium heart before it could burn further. The stolen envelope was ejected into space, leaving this low-mass core to collapse into a premature white dwarf. Some theories suggest this drama was part of an even more complex past, involving a third star in a destabilizing dance that ended in a merger, further complicating the stripping process. Yet the plot thickens with a second, equally puzzling signal. Despite its diminutive size, NLTT 11748 possesses a surprisingly strong magnetic field. This is deeply unusual. Low-mass white dwarfs like this are not expected to be strongly magnetic. Their formation pathway does not typically involve the core dynamos or mergers thought to generate such fields in their heavier cousins. So where did this magnetism come from? One compelling possibility is that the magnetic field is a direct scar from the traumatic merger or common envelope event itself. The violent churning and shearing of plasma during that catastrophic phase could have amplified a weak seed field into the substantial one we detect today, like stirring a dynamo in the chaos of a stellar death spiral. An alternative, equally fascinating idea flips the script on cause and effect. Perhaps the magnetic field is not a product of the merger, but a key actor in the star's present appearance. Strong magnetic fields can alter how heat escapes from a white dwarf's interior. By channeling energy flow and suppressing certain types of convection, the field could act as an insulating blanket, slowing the star's cooling rate. This would make NLTT 11748 appear hotter and younger than its true age, throwing off our estimates of when the dramatic interaction actually occurred. We are left with a system that is a living fossil of extreme stellar interactions. Its low mass tells a clear story of loss, but its magnetic field adds a layer of mystery to that story. Is the magnetism the roaring finale of a past cataclysm? Or is it a silent, ongoing force dictating the star's slow fade into darkness? Each observation of this binary pair is an attempt to read two signals at once, one written in absence, the other in persistent, unexplained force. 25 signals, each a question carved in light and gravity. Yet the true lesson of these stellar enigmas is not in the answers we have found, but in the certainty of mysteries still to come. For every pattern we decode, the universe seems to generate a new anomaly, a fresh signal that slips through the cracks of our understanding. This brings us to a final, forward-looking enigma, a placeholder for discoveries that will not just add to the list but shatter the categories we have built. The next generation of cosmic observatories is poised to transform this field from studying individual curiosities to mapping an entire population of the dead. The Vera C. Rubin Observatory, with its relentless all-sky survey, will monitor billions of stars, catching the subtle flickers of thousands of white dwarfs in real time. Meanwhile, the Square Kilometre Array will listen with unprecedented sensitivity, tuning its vast ear to the radio whispers of stellar corpses across the galaxy. Together, they will not just find more of the known puzzles, they will almost certainly unveil phenomena for which we have no current name. Imagine a white dwarf that flashes a perfectly timed optical pulse like a lighthouse, yet shows no trace of a strong magnetic field or a binary companion to power it. What internal engine could possibly drive such a clean, solitary rhythm? Consider the chilling possibility of coordination, not from one star but from several. What if multiple, widely separated white dwarfs began pulsing in an identical, synchronized cadence, a pattern implying not isolated chaos but some unseen, galaxy-scale connection? Or perhaps the signal will be written in a language we have not yet learned to read, an emission at the precise wavelength predicted for a theoretical particle, or a signature of dark matter annihilating in the star's dense heart. The greatest signal of all will be the one that does not fit. It will be the data point that resists every existing model of accretion, magnetism, merger, or planetary destruction. It will be the observation that forces astrophysicists to put down their textbooks, not to reference a chapter, but to draft an entirely new one. The 25th signal is the promise of the utterly unexpected, a reminder that the universe's most compelling messages are often those we are not yet prepared to hear. The white dwarfs have spoken, and their final word may be a revelation that rewrites the last chapter of a star's life, transforming our map of cosmic endings into a portal to discoveries we cannot yet imagine. These 25 signals are not isolated curiosities, they are a chorus. Together, they redefine a white dwarf from a silent gravestone into the universe's most extreme forensic laboratory. Each flicker of light, each whisper of heat, is a piece of evidence in an ongoing cosmic investigation. We have seen them become tools for remote planetary geology, allowing us to dissect the crusts of vanished Earth-like worlds. We have watched them forge magnets of unimaginable power and clocks of relativistic precision, testing the laws of physics under conditions we can never replicate. And we have witnessed the dynamic, chaotic afterlife of solar systems, where giant planets survive, asteroids collide, and dust clouds swirl in patterns of beautiful, unresolved chaos. This journey reveals a fundamental truth about our universe. The end of a star's life is not an ending at all, but a transformation into a new phase of complexity and revelation. The quiet, fading ember is an illusion. Beneath that serene glow lies a realm of ferocious magnetism, gravitational intrigue, and the scattered remains of entire worlds, each holding a story. These 25 puzzles are not dead ends. They are active frontiers, each one a question being pursued by scientists right now, using data streaming from telescopes both on the ground and in space. The next chapter in this story will be written by their work and by the curiosity of everyone who looks up and wonders. So tell us, which of these cosmic signals captured your imagination the most? Was it the planet being shredded before our eyes, the magnetic monster spinning faster than a kitchen blender, or the ancient star slowly crystallizing into a planet-sized diamond? Let us know in the comments below. If you want to join us for more deep dives into the universe's greatest mysteries, be sure to subscribe. And the next time you gaze at the night sky, remember that even the faintest, most steady point of light might not be a peaceful star at all. It could be a white dwarf, a stellar ghost holding the profound and active secrets of cosmic death, rebirth, and everything